This video is on electric potential. The electric field E at a given location is the electric force F felt by a particle at that location divided by the charge Q of the particle, and the equation that illustrates that is right there. Based on part A, why does it make sense that the electric field is a vector quantity? And that's because if you multiply or divide a vector, like F, by a scalar, for example, Q, the charge, that's going to give you another vector. Similarly, there's a mathematical relationship between what we call the electric potential at a given location, and that is the potential energy possessed by a particle or a charge at that location divided by the charge, as shown in this equation. And why does it make sense that electric potential is a scalar? Well, because energy is a scalar, charge is a scalar, so the potential is also going to be a scalar. The unit for potential is the volt. This is one of those comparatively rare cases in physics where the variable and the unit actually have the same symbol. Very, very rare. Energy is in joules, as we know, and charge is in coulombs. So 1 volt is also a joule per coulomb. If we took those two equations we wrote earlier and put them in no denominators forms, this is what they would look like. If we want to know what the potential is at a distance r away from a point charge, we use this equation right here, where the sign of the charge is identical with the sign of the potential. For a negative charge, it will be a negative potential. For a positive charge, it will be a positive potential. For a collection of point charges, the total potential at some specific location is found via the principle of superposition, where we must take into account the sign of the V contribution from each charge, but we don't have to worry at all about the direction. And that's because potential is a scalar, so we don't have to worry about direction. Potential difference, also called voltage, is measured using an instrument called a voltmeter. When using this instrument, we are always measuring the potential at the red lead with respect to the black lead, i.e. the black lead, or the COM port, is assumed to be 0 volts. This notation means the potential at Y with respect to the potential at Z. If B equals black and R equals red, the notation that would apply here would be the potential of the red lead on our voltmeter with respect to the black lead, with the black lead being 0. All right, suppose we wish to determine the potential difference between 2 points, but we don't have a voltmeter. But we do know the value of the electric field at every point between O and P. Let's call this function E of R. The path integral that we would have to solve is we would have to integrate the electric field at every point along the path. There's a little vector right there. And I just put the magnitude of the potential, which is good enough for what my purposes are. If we know the electric field at every point, we can integrate it along the path length to figure out what the potential difference is between points O and P. And of course, if the electric field is constant, then we pull the electric field out of the integral, and then you integrate dr, which is just r. And this is similar to an equation that we have run into with regard to capacitors. The potential difference between the plates of a capacitor that are separated by a distance d is E times d. That's the identical equation right there. All right, let's back up a minute. Suppose we have an acceleration function, and I changed it into its negative power form. The velocity would be the integral of that. So if we integrate that, the power goes up by 1, and then we have to divide by -1. We would end up with this. And then we have a c there. And the reason we need that c is because if it's an indefinite integral, we have to put an integration constant on there. That is going to be relevant here because it relates to electric field and voltage, as we'll hopefully see in just a second. All right, so let's say we have a solid metal sphere. So this is a cannonball here, and it's got a net charge on it, a radius of r. What's the electric field within the sphere? 0. All the charge is on the surface, and the electric field inside is 0. What's the electric field outside the sphere? Well, that conforms to the familiar equation kq over r squared, little r squared. Excuse me, sorry about that. Boop, there we go, little r squared. So little r is, something out here. All right, the further out we get, there's the magnitude of the electric field. All right, let's relate here the electric field to the potential. What's the potential for this sphere for r less than big R and for r greater than big R? I think what we want to do here is we want to say for r less than big R, that is inside, don't we know that the electric field is 0? Well, now look at the equation in the upper right. To find the voltage, we have to integrate that. Well, if you integrate 0, you get nothing except an integration constant. So we don't know what that value is right now, but we know that it's a constant. If we want to start graphing here, down on the bottom of the screen, for r is less than big R, the electric field is 0 right here, and the voltage or the potential is some constant number. Now we don't know what it is, but we know that it's some constant. So far, so good. What about when we get outside the solid metal object, the cannonball? We established on the previous page that the electric field was kq over r squared. And when we integrate that, here's the equation again in the upper right. When we integrate that, aren't we going to end up with a magnitude of v? That r in the denominator, it won't be to the second power, it'll only be to the first power. So that means in our graphs here, the electric field spikes up, and then it's going to swing down like that, proportional to 1 over r squared, not equal to, proportional to 1 over r squared. And our voltage is going to taper off, but not as rapidly. You can see in the equation that it only tapers off, it's proportional just to 1 over r. So it decreases also, but not as rapidly as the electric field. So there's a little bit of a connection there between the electric field and the potential.